Hey guys, this week we are going to be talking about data analytics strategies using multiple regression. Just as kind of an overview of what we're going to cover this week, there are 5 primary questions that we're going to address both in class and in this video here. These are research questions answered by B or beta. We'll talk about what those are in just a moment. Hierarchical analyses in regression, and there are 2 kind of basic flavors for hierarchical analyses that we'll talk about. Examining sets of independent variables. Some of this actually might sound familiar to you. This was a question that actually came up in class a few weeks ago, and so we're going to address that today. Looking at significant tests for sets. This is something that we will do in class this week. We're going to walk through examining significant tests for various independent variable sets and how that can be important for both mediation and moderation, and then inference strategies in regression to kind of wrap this whole thing up. So let's start by talking about the research questions that are answered by B or beta. Increasingly, people are becoming more interested in not just talking about whether there was a positive or negative direction in some sort of association between 2 things, but whether or not that positive and negative direction has any, and whether it's significant, but whether or not that positive and negative direction has some sort of true meaning, and if that meaning is consistent across other samples. Remember that when we're doing any type of analysis, we're assuming that we're drawing some sort of a random sample, but we can never be sure that the results that we get from that sample, A, are truly applicable to the broader population that it was drawn from, and more importantly, B, to the population at large. So for example, I study alcohol use and alcohol-related consequences, and I may find a relationship between alcohol use and consequences that has a standardized magnitude of, let's say, 0.3, a correlation of 0.3, and that's actually fairly consistent finding. But sometimes I find 0.2, and sometimes 0.4, and sometimes 0.5, and sometimes 0.15. So it varies, and that's an important point, is that every time we find a coefficient, a relationship, that relationship is only one of a variety of potential relationships. Remember when we're talking about both when we're talking about relationships, but also models in general, there's an assumption that our data are drawn from some larger population. So when you think about alpha and what alpha is and what a p-value is, we want to say that a p-value is telling us that some relationship is statistically significant in the p-value proves that it is, but really what it's saying is that we found this given association, and based on the alpha level that we've set, there is an X probability, whatever that probability is, that this sample falls within the tail of the distribution, right? Like there is a probability that the sample, or that this association that we found is completely untrue or completely spurious, and there's a probability that it is not. And so what we're really looking at is that probability that this is not in the tails of a distribution, that this is not an aberrant occurrence. Regression coefficients. When we talk about regression, we talk about these coefficients in terms of the causal effects that they have. We are assuming that there is some sort of predictive power of the variables that we have, the independent variables that we have in our model, and that predictive power is somehow associated with the dependent variable. This does not speak to the theory behind any type of analysis that you're doing. It is very much a causal approach. We are saying that this X variable predicts this Y variable and not the other way around. You can examine whether or not Y predicts X in alternative types of models, but usually the way to really show this is through some sort of methodological approach, not statistical approach. When we talk about our regression coefficients, we have both B coefficients. Those are unstandardized slopes, right? And those wind up being the change in Y when we have 1 unit change in X. That's what B means. Now the problem is B can be variable based on the scale of our X variables, the scale of our Y variables, and not every variable that we have is scaled the same way. Now, in the research that I do, oftentimes my Y variables are scaled as numbers, like 0 drinks, 1 drink, 2 drinks, 3 drinks, etc., or number of problems that a person has. In that case, the scale is easy and it's easy to follow, and sometimes standardizing, you lose what the real meaning is there. In contrast, sometimes I will ask on a scale of 1 to 10, how impulsive have you been feeling today? And people rate their impulsivity, and then I say on a scale of 1 to 4, how much negative affect have you had today? And they rate their negative affect. And so now we're talking about this kind of weird spot where it's almost subjective between people, how they interpret the 1 to 4 scale and the 1 to 10 scale. And B starts to lose meaning. If we could all standardize B and all use the same scales, then we would have some true meaning, and it would increase the scientific validity of the research questions that we're asking. Unfortunately, we don't have that in most cases in psychology. And so we wind up oftentimes using something that is more understandable, and that is beta. Beta is this little character right here. And beta is a standardized regression coefficient. So recall when I showed you this in class a few weeks ago, if you do a regression model and you ask for the beta coefficients, in a bivariate model with just one predictor variable and one outcome variable, beta is equivalent to the bivariate correlation. And so as we add increasingly more variables, beta becomes no longer the bivariate correlation, but it becomes a part and partial correlation based on the other variables that are in the model. Part or partial, sorry. And it tells you the standardized variance accounted for. You can square beta and you will get variance accounted for after controlling for everything else in that model. An alternative approach is to simply convert all of your scores to z-scores. This is nice in that it standardizes everything. It standardizes your slopes, or standardizes your predictors, and it standardizes your outcomes. Unfortunately, you lose any type of real scientific validity. So if we said that people are rating their impulsivity on a scale of 1 to 4, and we use that to predict the number of drinks that we have, and we get a slope of 0.7, then we know that for every 1 unit increase in impulsivity, we see an increase of 0.7 drinks consumed, right? With z-scores, you don't get that. That meaning is lost, and instead it's a magnitude of relationship. And so in this case, you might find if the actual beta score was 0.7, then you would say that the standardized relationship between impulsivity and alcohol use was 0.7, or you might say that the variance accounted for in alcohol use is 49% based by impulsivity. So they have obviously some very different meanings, and within that context, you can't change them. We're going to do this in class. Or you can't compare them. In class, we're going to convert our variables to z-scores, and we're going to look at regression both using z-scores and not using z-scores, and also look at correlations using z-scores and not using z-scores. What you're going to find, interestingly, is that if your dependent variable and your outcome variables have been transformed to z-scores, then it is exactly the same as running a correlation analysis and getting a correlation coefficient. Recall that one of the steps in calculating a correlation coefficient is converting our scores into z-scores, right? So we will do that in class and have a look at that a little bit this week. Okay, let's talk about hierarchical analysis and regression. So when we talk about hierarchical analysis, and I'm not talking about hierarchical linear modeling, also called multi-level modeling, what we're talking about here is simple adding sets of either sets or single independent variables in steps. And so in your book, they talk about the importance of causal priority for the removal of confounding variables / variance when you're adding sets of or variables into a hierarchical regression analysis. What we often see is that, and this is when we'll walk through this in class. This was what we were doing a few weeks ago when I put a variable in step 1 and then I clicked to step 2 and then I clicked to step 3. And as you do that, as you click from step 1 to step 2 to step 3, you're entering either single variables or variable sets. The primary reason to start with that is to remove any type of confounding variables and or to control for spurious associations. And second is to give priority to the true causal variables in the model. The causal variables have to do with the basic research relevance, right? Your book makes a case for ordering your variables in your steps in order of the hypothesized effects, because you can, as the chapter later points out, have very, very high numbers of independent variables. And in fact, sometimes we have a ton of independent variables and we don't know exactly which way these things should be entered. There are a number of different ways to enter your independent variable sets. My preference is to enter demographic variables first and examine the variance that's accounted for simply by age, biological sex, and so on. Other people will say that those are not as pertinent to the research question, and they will add those as a final set. There is an alternative approach to this, which is called stepwise analysis. And we will walk through doing stepwise analysis in class this week. But stepwise analysis assumes that you have some large number of independent variables with very little theory or no theory to guide what variables or what steps of variables should be added. In stepwise analysis, you can do a few different things. You can enter all of your variables and have the model go through and selectively choose the variables that capitalizes on the most variance accounted for in Y. This is an empirical approach. It is not a theoretical approach. There are varying opinions on this. I will tell you my opinion is that this is a poor approach to building models. This is an approach that's often used in genomics, especially data that has huge amounts of predictor variables or potential independent variables. We're going to walk through it in class, and I'm going to teach you guys how to do this, and then I'm never going to test you on it, and I hope that you never actually have to use this. Maybe somebody will prove me wrong and find a good approach for it, but it's not a theory approach, which means within the realm of psychology, it's not ideal. It can be okay in the case of entering a situation where you have no idea what's causing something, but you have a bunch of data and you want to try and find a potential idea. So sometimes it's used as an exploratory technique, similar to exploratory factor analysis. All right. Moving right along, let's talk about independent variable sets. A set of independent variables are any type of ordering or group of variables that have some sort of link to each other. There are two basic types of sets of variables. We have structural sets and we have functional sets. Structural sets tend to be sets that have no meaning outside of themselves. So, for example, the most common structural set that we see is categorical variables that have been dummy coded for one way or another. So for example, I do research using 3 conditions oftentimes. I'll have a control condition and then 2 different types of intervention conditions. And in order to do that, in order to look at that, you can't just order those as 0, 1, 2 or as 1, 2, 3. That has no real meaning. What we really want to do is be able to compare across those. And we're going to do this in class. I'm going to walk through a structural set and a functional set with you guys. Structural sets, in this case, we would have 0 being coded as anything that is that is one of those groups. And then let's start over. If you have 3 conditions, then you are going to have g minus 1 variables in your structural set. So for example, if I have intervention 1, intervention 2, and control, I will have a variable for intervention 1 that is coded 1 for everyone who got intervention 1, and then 0 for everyone who got intervention 2 or for anyone who got the control condition. I will also have a variable coded 1 for anyone who got intervention 2. And then it will be coded 0 for anyone who got intervention 1 and anyone who got the control condition. We just have 2 predictor variables, and then we will enter those in the model together. The 0 group, the control group, winds up being our base comparator group in this case, and we have each coefficient then within this group only has meaning relative to that 0 group. And so the slope of intervention group 1 will wind up being the difference in intercept or slope, depending on whether there's an interaction or not, relative to the control group, and intervention 2 will be the difference relative to the control group in intervention 2. We'll walk through that. I know that it doesn't have a ton of meaning as I'm saying it here. We also have functional sets, and functional sets tend to be variables that are, for some reason, interrelated. They have some sort of functional or theoretical link. And a good example of that is subtests for an IQ. So if you have, for example, digit span and word processing and I don't know, some other some other type of, here's a better example. Let's say that we have 5 different aspects of impulsivity: positive urgency, negative urgency, sensation seeking, conscientiousness, and perseverance. We might say that all of those are functional sets of independent, or a functional set of independent variables that should be entered together. And so we might say at step 1, we entered age and biological sex to control for demographics. At step 2, we entered the functional set for impulsivity, which was these 5 variables: positive urgency, negative urgency, and so on and so forth. And so that would be an example of a functional set. In contrast to structural sets, or in contrast for a structural set, we might say in step 1, we added age and biological sex, and in step 2 we added the 2 structural sets or dummy coded variables for our treatment, 2 treatment conditions, or something along those lines. Typically in a manuscript, we would describe what we're going to do in our analytic plan before actually doing it. That is really the difference between structural versus functional in simultaneous and hierarchical analysis. Next comes the proportion of variance for sets. And so we have within the kind of confines of this, after each set, a change, and we will get a test, a statistical test of the change in the predictive value of our model based on the set that just completed, as well as the semi-partial R squared for that set and the increase in overall R squared by adding that set. Remember, R squared is linear, which means that adding a set only increases our predictive model, or will increase our predictive model in a linear fashion, assuming that that set has some sort of relevance or statistical significance, which we'll talk about here in just a second. Within each set, you can compare your betas and your beta weights. Note, though, the final set will actually give you a complete model that has all of those variables entered into the model with everything partialed out or controlled for. So you will get a comparison of set 2 to set 1, or after controlling for set 1. And this will make more sense when we do it in class. All right. We also get significant tests of our independent variable sets. We get this by examining increases in R squared and the extent to which a set increases R squared total. Again, R squared, I covered this a little bit on the last slide, but R squared winds up being a linear increase, or a proportional increase of the linear R squared, linear variance accounted for based on the variance that was already accounted for in the previous set. In hierarchical analysis, we will have something like at step 1, we entered, biological sex and age, and these were significant predictors of our outcome variable. And we will provide F, and we will provide an R squared, an overall R squared of that set. We might also provide the slopes, either standardized or unstandardized, for each of those predictors. And then we would say in step 2, we added blah, blah, blah to the model. This resulted in a significant increase in R squared, or a non-significant increase in R squared. We'll also get an F test for this, as well as a proportional test of the increase in R squared and whether or not it's increased significantly, or statistically significant amount of variance accounted for. You also don't have to enter things in sets. You can do it all in a single simultaneous analysis. When you do it this way, it allows for the partialing of a single variable of interest all at once. When everything else in the model is accounted for, you will get a single F test instead of multiple F tests. You will not get changes in R squared, but you can, using this approach, pull out or partial out the proportional amount of variance in R squared. You can also do something very interesting in this approach, which we'll talk about in class. I'm not going to go into it right now. All right, so lastly, the book talks a little bit about this piece, right? Statistical inference strategies in multiple linear regression. For the most part, less is more. Remember that every time you add a predictor variable into your model, every time you add a new independent variable, you increase the probability of a type 1 error. Even with high N, even with a lot of people, where your standard errors become more precise and your point estimates become more precise, the more predictors in your model, the more likely that you will stumble across a spurious effect. Conversely, the fewer predictors that you have in your model, the more likely you are to not find the hypothesized effect that you assume would happen, because there is more noise, right? So research in many fields, psychology being one, especially the softer fields, oftentimes winds up being our attempt to strike a balance in the most appropriate model. In regression analysis in the behavioral sciences, parsimony is key, and your authors in the textbook suggest using the least is last approach. This means that in a regression analysis, your best approach is to enter the variables that are least associated with your hypotheses as the final variables in your model, and the most important variables entered early on in the model. This, of course, has to be balanced against the possibility of confounds that you want to remove before looking at the hypothesized effects. But okay, guys, that is it for today. We will be talking about sets this week. We will be doing stepwise regression, and I will walk you guys through basic hierarchical regression analysis. I will see you all Thursday.